This is the Math Map Book Club, where ordinary parents encourage one another to develop an extraordinary appreciation of math. We love what we know and struggle over the unfamiliar. Through weekly conversation and exploration among friends, we can begin to enjoy ideas that seem difficult. Join our book club as we discover how math helps us to know God and to make Him known. It's Wednesday, December 18th. Welcome to the Math Map Book Club, where Kirsty Gilpin and I discuss lessons each week from our math curriculum for families with students enrolled in Classical Conversations communities. This is our last Q&A of the wonderful 2024, and we look forward to seeing all of you again in January. So, Kirsty, what do you have for us today?
Well, hopefully just some fun and good questions. So this is our third Q&A call. And so we want to start off by giving you guys a chance to ask your questions. So did anybody come with questions today that you'd like to get answered?
Well, I brought something, but I don't, if anybody else has anything, I'm going to wait.
All right, sounds like it's all you, Jana.
Okay. Well, I have just been loving the charts. It's in several different places where you have all of the functions, like linear and quadratic, and then you have the signs, the trig functions, and all that stuff. I like what I think of as almost like a chart A for the functions. And I've been noticing more and more patterns with them. I will tell you, the first time I saw all of those in one place, it was so much, I could hardly take it in. And I wondered if you would spend a little time just looking at those and letting us compare them more, and maybe telling us, like, again, what the A stands for and what the K stands for and what the H stands for. And just, there's so much beauty in that page, and I just don't have a whole lot of understanding, but I see such potential there. Does that even make sense?
It does. It does. I am going to see if me pull up. Okay, can you see a pink screen now instead of the question screen? Perfect. So just like I love the fact that you said chart A, because one of the things that Lee has really tried to do is say how does this all boil down, right? So we have our 112 sentences, right? And we know you could combine those and do different things. But it gives us that basis on which everything else is built. And so the same idea with these functions is that this is the basis on which everything else is built. Because if I look at that group of functions, I might multiply functions, I might divide functions, I can add and subtract functions, and then I can do compositions of functions. So that would be like sine of x squared, right? Where I have one function inside of another function. I can have powers of functions. So there's all of these different functions I can create from these building blocks. When we look at the building blocks, the first ones that we see there are the power functions.
And which chart are you, or what are you, like, where should we look?
So if you want to look, you could look at, depending on what you have in front of you, right? You could look at chart 8.1. We list them there by name. We list them again in chart 11 with little pictures. We list them again in chart 13 with with their pictures and then their polar graphs. They're in 17. They're in 18 with all of the different transformations. 25 and 26 has the same list for derivatives and integrals. And then perhaps one of the most helpful is on chart 30, chart 3 of lesson 30, because that has the parent function, the integral, the derivative, and then also what the reflection would be. So I'm just pulling from my memoriam to talk about them in groups, but those are all the different places. So I'll just write that over here. So you could look at 8, 11, 13, 17, 18, 25, 26, and 30. are going to be your best places to look for this same list. So our power functions are any function where I have a variable as a base and I have some constant as my index, right? I'm just going to use a capital I to remind us that that's our index. And so I is my index and it is a constant, meaning it's a number. And so that number could be a natural number. It could be a negative integer. It could be a rational number, right? Those are, and we could have reals. We don't talk about those. We look at the case where you have a positive whole, a negative whole, or some kind of broken number, right? A fractional. When we look at that, we see that we have these basic graphs, right? And so going kind of quickly, if in this case here, right, if it's even, it's going to look something like this. If it's odd, it's going to look something like this. The higher the index, the narrower that's going to be. If, let's use a different color. If it's a negative, we're going to see that it's going to look something roughly like this, right? Where my denominator isn't going to be equal to 0, and so we're going to use asymptotes, right? And so we'd have an asymptote. If it was fractional, we're going to see that's where we're looking at roots, and we're going to look at something that looks like this if it's positive, because if it's even, we can only look at positive roots in the reals. If it's odd, it's going to be two-sided and go a little bit this way. If it's both negative and fractional, we're going to see that it actually is going to sort of follow the graph of the negative more than it does the positive, right? It'll look more like the negative graph that sort of trumps the positive. Those are what we call the parent functions.
Wait, back up on that fourth one. You went too fast for me. So what do you mean by the more like the negative shows? Like point to it with your cursor.
So if I was to look, if I said, like, I'm just going to make one up, right? So let's say x to the negative 1/2. We're going to see the graph is going to be more like the red graph for the negative than it's going to be the 1/2.
Which is the blue one.
Sorry?
Which is the blue graph.
Which is the blue graph, yes.
Okay, I followed.
So these are all parent functions. And so in general, they're going to be centered at the origin. And there's going to be no dilation, meaning that my scale is 1-to-1. I haven't done anything to it. All of these can be transformed. And so when I transform something, I have some options. I can shift things up and down. I can shift things left and right. I can dilate, right, which means I'm going to make it bigger. And when I say bigger, smaller, that's really what we're meaning, but it's also an away from or a toward the origin. So I'm going to kind of say that. So away from, in coordinate plane, it's going to be away from or toward the origin. If it was not in the coordinate plane, then we would have a center of dilation that would sort of describe that. And the other thing that I can do is I can reflect, right? And in general, we're going to be interested only in the case where we reflect across the x-axis or the y-axis. And so I'm just going to move this up a little bit. Well, maybe, there we go. Right, so this is across x or y axes. So when you were talking about the A and the H and the K, that's where this comes in. So my up and down shift is my K. My left and right shift is my H. And my dilation and my reflection are my A.
Okay, so you're shifting up and down. That would be like your Y value.
Yes,
Left to right would be your X value.
correct.
And where are the X, K, and A coming from? Or H?
So those are, so I'm going to show you now how those fit in. So we go back to our um, our general form here for a power function. And what I do is I say, okay, if I'm going to shift it left or right, I'm changing my X value. So my H goes with my X. And now that's a group, right? So I'm going to use parentheses to say this is my group. So now this is where my index would be, right? Whatever my index was, it's going to be there on that whole group now, not just on the X. My K goes with my Y. So if this had been written as Y equals, I would have done Y minus K. But because we often use our f of X, we're going to move our K over to the other side. So if this was Y, right, Y minus K equals some function of X, right? Y now is going to be that, whatever that function was, plus K. Right, which is why I have a minus with my X and then a plus K, because
Yes.
I've moved it from one side of the equation to the other. And then I say, okay, well, if I'm dilating this or reflecting this, I'm going to put that here next to this term here. And so this is now what we call the general form of the power function. And what this is this is all the possible power functions that I could create, right? So you could pick any index, and then I can center that anywhere in the plane, and I could grow it or shrink it or reflect it, right? Whatever I want to do to it, that's going to be what that looks like. So for any
Question.
index,
Over your reflection across X or Y, why didn't you include the origin? Because that includes both of them anyway?
it does. So the origin would be
Okay.
across the X and the Y.
And the Y, okay.
So, and usually when we write it this way, by the time that negative gets pulled out, it's usually we're reflecting it across the Y by the time it gets pulled here. So if we saw this equation and it was negative, it would look like a reflection across the Y because of the way that dilation sort of works its way out by the time we write it as A.
So, oh, yeah, go ahead.
Yep. So that's all, every possible power function can be written is represented by that general form. So your question, Dana.
Well, I was just going to say, so let's take, we all memorize the slope intercept form for linear
Yep.
functions. So if I've got y equals mx plus b, what are the m and the b? How is that?
So what would be our parent function? Our parent function would be the simplest possible function. So that would be y equals x.
Okay.
Okay. So now if I said to you, I want to shift it up or down, right? So that would be my y-intercept. Here, my y-intercept is at 0.
Okay.
Right? So I'm
Yeah.
going to shift it up or I'm going to shift it down. And so that's going to be my B, right? So this is like my K.
It's okay. We're just using a different letter
We're
to,
just using a different letter.
okay.
The slope becomes like my dilation, right? Am I stretching it this way or am I stretching it this way? That's what that M is like. It's kind of like my A. Now, if I was to write this, I could have said that this is my M or A times X minus 0 because I'm not shifting it left or right. plus my b or plus my k. And notice that here's my index, my 1 didn't change because it's a linear function, so that didn't change at all. Now, with lines, it's a little bit different because I could have shifted it left or right, multiplied it by my slope, and then I'd end up with my vertical. Like they're so intimately connected in my linear functions that it can look, I can say I've shifted something left and it would have a corresponding shift up or down, right? I could say that this left is the same as this shift down, up or down based off of my slope. So my linear function, it's a little bit harder sometimes to see both pieces, right? The way that you would with the exponential or the quadratic, right? There I might be able, it's a little bit easier to say, oh, it went left 2 and up 3. With a line, shifting it left,
Yeah.
right, is the same thing as shifting it left is the same thing as shifting it down. So did I go left 1 and down 1, or did I go up 1, right? So it's a little bit different. We don't always see both the horizontal and the vertical when we're looking at lines. We tend to just see it as a shift up or down, hence the B.
That might help you over time for those that really want to understand it, is to take those charts Kirsty listed and make them longer, because among them you'll get various uses. So some of them concentrate on the parent function, some of them concentrate on the general function, some of them concentrate on the common one that matches the graph that's on the page. There's no way on one page to show all the variations. And so we've done examples of variation, particularly in week 18, where transformation is the topic. But what Kirsty had us do in the chart in 18, you could do for almost any other equation you made up. And so to really understand it, it would be good to make a much longer chart. But I wouldn't ask your children to do that until they really get the idea of this general equation and how I has 4 choices, and that H means left and right, and that K means up and down, and that A means I'm scaling it somehow. Like get the basics and then start integrating all the details.
So Lee, are you saying that like to take, 8, 11, 13, 17, 18, 25, 26, and 30, and then find the chart and then put them all side by side, laying them out that
Yeah.
way?
And then you'll see repetition, so you can eliminate those columns, and then you'll see subtle differences. You might want to keep those columns.
Okay. Makes sense.
So what Kirsty did is for each lesson, except for 30, tried to do what was the most important for that content, even if in complex you're not seeing it quite yet. We're going to get you there. But once we get to 30, we tried to summarize what I just said. But once again, we were still limited because our paper's only so big.
Yeah, I love this chart in 18. I hadn't seen this one yet. But yeah, I see what you're saying. And they're under the linear graph. So when you rewrote this slope intercept form, when you put x minus 0, that's the 0 is actually the h.
Yep.
Yeah. So okay.
And even 17 on chart 2, that's what I went to when we just because I was just trying to find where the A and the H and the K were. And it's there too, with the line graph is showing all the exponents. So that was kind of helpful. But I like having the list. So thank you.
Said,
So I'm
use
just,
the general equation, plug in whatever you want, and then plot it. And you would have come up with all of linear algebra on your own. But most people don't want to do that. So we went to what are the 16 most common parent functions that represent the majority of equations you would do at this age range, and then showed you how to tweak them differently on different charts. Is that fair, Kirsty?
yeah. So, and that's to that point, right? So we just talked about the power function and we broke it down and we said, hey, let's look at some examples of that power function. But the cool thing is that when you think about the power function, it doesn't matter what that index is, all of those power functions are going to behave the same way. They're all going to be transformed the same way. They're all going to be differentiated and integrated the same way. That the same rules apply to all of them. Now, the other big buckets that we have are the exponential, and I'm just going to show here the exponential and the logarithmic we put together. But the key here is that differentiates this from the power function is that here I have some constant base, and this time it's my index that is the variable. Right? And so, or in the case of the logarithmic, it is the power that is the variable, right? So here, my x is my index, and my y is my power. Here, my x is my power, and my y is my index, right? And so that's how we can see that these are inverses of one another because we swapped our x and our y.
Are you guys comfortable with seeing f of x and immediately going to y and vice versa? Because that's really important for algebra to make sense. If you, that's like a test. If your child can't make that leap, you probably need to just work on grammar and flashcards and the geometry and go back tomorrow or a week from now and look at the functions because that's really an important abstraction.
Yeah, so f of x is the same thing as y. And when you call them power functions, you're talking about your x having an index. So it could be a quadratic equation, it could be just a constant, it could be a linear equation. Any of those are called power functions because the exponent, or excuse me, the variable has an index.
Yes. So what
And
we're saying here is that the function is looking at the powers of x, right? We're examining the powers of x. That's why it's the power function.
Okay, and now that was a whole group at the beginning.
That was
and
that
now
whole group at the beginning.
And now you've moved down to what we call exponential functions.
Yes.
Now we've moved our variable x to be the index
Yes.
or the power. Okay.
Yes. And so now in this case here, notice we can still do all those transformations are still going to work the same way. So my base, if I'm looking at my exponential, right, here's my base is still going to be whatever number I choose. And then here, what do I put with my x? My h. Right? Where do I put my vertical shift? Out here, plus k. And then if I wanted to reflect it or scale it, I multiply it by a. So that a, that h, and the k mean the same thing on all of these, and are how we go from our parent function to our general function.
So basically your A is 1 and your K would be like your B or a constant, or actually back up in a parent equation, your A is 1 and your K is 0. And that's why we get lazy and we don't write them. And that's what causes children confusion.
They're hidden
They're
Yeah.
hidden. Yeah, that
because of
goes
the
back to,
identity law, right?
yep, that exactly. So we keep going back to, right, all of these hidden things that eventually we stop writing them because we know, but when you don't know, it makes it a lot harder to see the pattern. And so Lee's been trying to be very precise in particular about including those hidden zeros and ones.
So in year 5, 6 of doing the math map, 5 years down the road, when we come back to the very first lesson, which is our, getting our mind wrapped around just the hidden zeros and everything, we could be talking about this maybe with those more advanced students that have seen this again and again and again, and let's see where some hidden zeros are in these functions.
Absolutely.
Okay.
Yep. So that's our exponential and logarithmic functions. And then our next bucket of functions are our trig functions. Okay. Now the trig functions are really neat because they're cyclic. Everything else, right? Just like as if you go from negative infinity to positive infinity on your x-axis, there's not necessarily a cycle or a pattern to it, right? It starts here and it's changing and it ends up over here. Our trig functions all have a period and they all repeat. But whatever they are, so I'm just going to look at sine, for example. Okay. When we look at sine, the same thing happens. I can take that's my parent function, and I can say I can shift this left or right. I can shift this up or down, and I can dilate or reflect this. And so my A, my H, and my K still mean the same thing for all of those.
I love math.
And so we have our 6 functions there. Once you get to lesson 16, you start to practice that, you're going to start to see the relationships between those functions. So for example, if you think about a right triangle, right? If this is 30 degrees, what's this over here? 60, right? If I look at the sine of 30, it's my opposite over my hypotenuse, right? Whatever that is. But if I was to look at the cosine of the cosine of 60, I would see that my adjacent is the same as my opposite side over my hypotenuse. And so that's where I see that my sine, in this case, the sine of 30 is going to be the same as the cosine of 60, which is the cosine of 90 minus 30. And so we're going to see here when we look at the graphs of sine and cosine, that my sine graph looks like this. My cosine graph has a 90-degree shift. And so it mirrors it, but just shifted 90 degrees because of this. Then our tangent is sine over cosine. So as we start to look at the sine and the cosine, we start to see some relationships between that and the graph of the tangent. And then our other 3 trig functions that we look at, the secant, the cosecant, and the cotangent, are their reciprocals. And so if we learn the sine function well, right, and when we start to see this relationship between sine and cosine, we can take that sine function and we can see how that sort of flows through those other functions, right? We're presenting them all individually so students can just use this as grammar work. But eventually, as people get really familiar with these, they're going to start to see, oh, like if the more I know about my sine curve and my sine function, that's going to be instructive for understanding all of these other functions. And they're all going to behave the same way with these transformations.
Wow.
So then there's 2 more that we can think of. We're going to talk about relations, and we're going to look specifically at some conic relations, some conic sections or conic relations. So a relation is the broad bucket from which we pull the functions. So remember that a function, when we talk about a function, we say that, oops, that works. We have 2 sets, and each x goes to just 1 y. Now I might have more than 1 x that goes to a y, but there's no case where 1 x goes to 2 y's. So when that does happen, that's when we say we're talking about a relation. That's really weird. The autocorrect is making them triangles, but in this case, right, I might have this same value goes to two y values. It might go to 1, but it can go to 2. And so if you think about a graph of a circle, for example, right, if this x value is going to map to this y value and this y value. So it's not a function, but it is a relation. And we look specifically at the conic relations, the conic sections. And so let's talk about the circle. Right? A circle says that our equation is x squared plus y squared equals r squared. Right? Well, notice that I can say, if I wanted to move this, x minus h squared plus y minus k. Now I'm putting it with my y, so it's minus again, because I haven't moved it, right? Equals r squared. And then if I wanted to dilate it, this is where it gets a little bit weird, because we would want, if we wanted it to still be a circle, we would probably just change our radius, right? If we started dilating it, if we were to dilate it by just applying that to one of our one of our variables, we'd end up with an ellipse, right? Because I would stretch it one way or the other. So I would either want to say, hey, both of these being multiplied by some scale factor, or if not, I'd end up with an ellipse, right? And we would see the formula for the ellipse fall out from there. But that same idea of being able to translate and adjust. And then the last group of things that you see that we refer to is the piecewise. And I saved this for last because we always use the absolute value function in order to talk about what piecewise means, because I can talk about, it's a way to talk about the absolute value function, but also talk about piecewise functions. A piecewise function says take parts of other functions and stick them together. So if you think about the absolute value function, right, I could say that from negative infinity, right, less than x, less than 0, right, between negative infinity and 0, my function is y equals negative x. But from 0 to positive infinity, y equals x. So those are the two pieces that I can put together. Now, if you have students, or if you're interested yourself, if you go to, and you've heard us talk about Desmos before, desmos.com, it's essentially a really great online graphing calculator. If you Google it and I'm not sure exactly what you would put, but put something like competition with it, and you'll see that students, right, in classes across the country will take piecewise functions. We'll build these really elaborate piecewise functions that include inequalities and equalities, right, functions to create drawings, right? So for example, I might say, if I wanted to draw a snowman, right, I might just want small pieces of different values together, right? I don't want the whole line that goes here. Maybe I only want this portion of the line. And so whatever my picture is that I'm trying to draw, if I was trying to draw a house, for example, I might want to say, well, from here, I want to have this function, y equals 2x. Then I want y equals 2. And then I want y equals negative 2x. And then I want y equals 0. And there's part of my, right? And then I would define just define the domain for which I wanted to draw all of those pieces.
Could
Here
you
I might,
also say your limits? You could define the limits. When you
the
say define
limits.
the domain, you could also say, yeah.
So here I might say y equals 2x from 0 to 2. for example. I'm completely making this up, right? And then y equals 4 from 2 to 6. And then y equals negative 2x, but now I'd have to have some plus. I'm just gonna put b because I don't know what it would be, from 6 to 8, right? And so now I'm creating this piecewise where I'm taking all of these pieces and putting them together. And so that's what we mean, because we could use anything, right? I could have a, and here I might have different pieces so it's a relation, right? That's not, they're overlapping, but I might have said, I really want this to be a function. And one common function that is piecewise is the step function. And so it's this point, right, from 0, and then it steps up. And something like that, right? So there's these functions out there that put different pieces together, right? Because though this would be y equals 0 from 0 to 1. The way I've drawn it is like this. Then y equals 1 from 1 to 2. And so that's what a piecewise function is. And so that's why I saved it to last, because I wanted to point out I can take any of those functions I've talked about and I can chop them into pieces and put them together to create a piecewise function.
Computers know how to draw.
So can I say a couple things of really basic and you tell me if I'm saying them right?
Yes.
Okay. So in math, anytime you have an equation or even an equality, so you have either an equal sign or a greater than, less than sign, and you have an x, you have a variable. Anytime you have that in math anywhere, that is a relation. Yes? Okay. Sometimes that relation will be a function. If there's only one value that each x can be,
Yes.
that will be called a function. If x can be multiple things, then we don't call it a function, we just call it a relation.
Yes. But
And
just to clarify your language, it's not that x can be, but the x maps to, right? That my function
okay.
can be at x.
X maps to, meaning, okay, so meaning when we plug it into this equation, it will solve to one. I mean, is that
Or
So think
simplify
about the
to,
square root
yeah.
of 9. What's the answer to the square root of 9? Plus 3 or minus 3. So 1x has 2 answers.
1x has 2 answers?
So it's a
Okay.
relationship.
So that's a relationship, not a function.
Yeah.
Right.
Okay. Okay. So then, and every equation or inequality statement, whatever, can be drawn on paper, on graph paper, or so. I mean, I guess that you would have 3-dimensional. Would you have 3-dimensional?
Yes.
String of it. You can have 9 dimensions and
Okay,
draw
okay.
worms.
Right. But there's a picture, there's a physical drawing picture for every single equation or inequality.
So if you think about this, right, in 1D, if you said x is greater than 3, this is -1. Did I do enough? 0, 1, 2, 3, 4, right? We would graph this and we would say x cannot be 3, but it can be everything greater than 3.
Mhm.
In 2D, right? Let's say we'll just use the same thing, right? X is greater than 3. So, well, if I was to draw right, here's a line at 3, and I made it dashed because x can't be 3, but x could be everything greater than 3. So now I'm shading a portion of the plane. In 3D, and this is going to look awful, right? But now x equals 3 is going to be a plane, because here's my x equals 3, and it's going to be true for all my values of z and all my values of y. And so if I was to kind of have a dashed plane sort of that looks like this, right? Well, now everything where x is greater than, I would be able to sort of shade. So you can't see that, right? It's a terrible picture. But let me see if I can find my
It was
mouse
actually pretty
because
good.
and so that's going to be true for, let me do this, and that might help me see my mouse better. See if this will come up quickly enough to be able to show you. All right, so here's 3D. So let's say that I wanted y is greater than x. And here's the fun thing about Desmos, right? Is you can see that now I've got y equals x, and that's defining a plane in 3D, and then I've shaded all the places where that would be true. Only I would argue, right? And so now when I extend to 3D, you see, right? That's the whole 3D-ness of y is greater than x. But I can do this. This is really fun because I can do sine of x, right? And you can see now what does that look like in 3D? We can't, right? We could think through what would it look like in 4D, right? It would be the portion of 4D space that would be greater than that. But we can't actually draw
Depict it.
that easily, right? Because we don't have 4 dimensions that we can see. So this is really, I think, a powerful tool if you, especially you, if you have older students, but especially you, if you want to look at what does it look like for y equals sine of x, right? So we see if we were to look at this in 2D, right, we know that it looks, let me see if I can get to where it would be familiar. Well, just kind of
so
picture that,
badly.
right?
Yeah.
Right, you can sort of see there's our 2D. Well,
Mhm.
now I look at it from the side, and it's got to be true for all 3 dimensions. And so now I can start to visualize what does that look like. But now imagine if I said that z equals the sine of x minus the cosine of y. Right, now I can start making up some really fun functions in 3D and still get a picture of what does that look like. Right? Because that's really fun. Right. And so we can just play around with what does this look like in 3D? Because there's no way I could have drawn that, right? I can graph in 2D, but 3D having tools like this is going to definitely help us to make sense of that.
And it
So
only
be
goes up to
gracious.
3D?
Yeah, it only goes up to 3D because
Nobody knows 4D.
if we could, but now think about this, right? We could say that this is, if we said our 4D was WXYZ, right? Whatever our things are, we could say we live in WXY. And so I could say, well, I'm just going to pick those 3 variables to look at. And so this would be like the shadow of a 4D thing here in 3D, right? But yeah, we
Ooh, I
can't
like
really draw
that.
4D.
It's the shadow of it. Cool. That is good. Good insight, Kirsty.
It's just a quick side note on Desmos, like 3D, this is mind-blowing, but 2D is much, I think, much easier for us to grasp and for kids to grasp. And I've had my students before just play around. There's games on Desmos where they have balls that will drop and you're supposed to create lines, or like you're supposed to, there's stars on the graph. And so you have to write equations so that when the balls drop, they will touch all the stars. So it's like a they're
Maze.
Oh,
writing.
that's fun.
So
Yeah.
it gives them
Like a
kind
pool
of a, like,
table.
yeah, like I want to make a line that looks like this. So what kind of an equation do I need to write? And if it's not quite right, then they have to figure out which of those numbers do I need to adjust so that it will,
Mhm.
tip more, or yeah, be a little lower. So
Yeah, so you can see where knowing your A, H, and K would really help
Yes.
you, right? If I know my general shape and then I know where I want it to be in the grid, that
Right.
gives me a lot of power for being able to do that.
So Kirsty, this has been fabulous, but we only got 15 minutes left. And I want to double check. Does anybody else have other questions? But if not, you keep going. This is wonderful.
I had a question that kind of came up when we were talking. Inverse versus reciprocal,
Mm.
defining the difference between those two things.
Sure. So say that again, and I'm just going to clip. I have to find my mouse.
Okay,
There we go.
just the difference between reciprocal and inverse. I think I have a
Sure.
better picture in my head of inverse, like one,
Okay.
undoes the other.
So a reciprocal is a specific inverse, right? So let's look at inverse first. And an inverse says that if X goes into my box, right? And let's say that this is right like this, and then it was to go into the inverse, it would come back as X. So an inverse, just like you said, an inverse is an undoing, right? And it says whatever, if this is this is my function f of X, then this is my inverse function. And if I used both of those, I would end up with what I started with. Graphically, the way that this is also very closely related to the reflection across y equals X. I can always find the reflection of a graph across y equals X. Okay, so I'm going to show you, right, that was a bad choice. I'm going to erase this because that wasn't really what I meant. My hand did not do what my brain was thinking. Let's look at our quadratic function. And I'm going to draw my y equals X line. And then I'm going to draw, if I was to reflect this, right, each of these points, this is going to look like this. Okay. But if I was to look at this as an inverse, right, so my function is X squared. Here's my problem. So I put 3 into X squared and I get 9. But what other number could go into X squared and give me 9?
-3.
-3. So now if I take my 9 and I want to put this into my inverse, right, which if we were to solve for the inverse, we would get the square root of X. Well, notice I have two possibilities, right? I have 3 and I have -3. Well, if I started with 3, but then chose my -3, I didn't get back what I started. So there's not a true inverse. And so what you'll see in the charts frequently is we'll say, this is the reflection across the y equals X line, right? Because I can talk about what that reflection looks like, but it's not a true inverse. And so only some functions have true inverses. And those are, all right, so Jana, you're like, you've got your relations and then you've got your functions. Well, a one-to-one function says every X goes to one Y and each Y goes to one X. And those will have an inverse function. Now, a specific case, and this is where I said, when we think about the inverse, right, you think about, well, if I add 3 and then subtract 3, I get back what I started, right? And so that's where we call that the additive inverse, right? Because I'm undoing. But then we talk about the multiplicative inverse. And if I said I had x times n, well, the multiplicative inverse, right, would be 1 over n. And so this has a specific name. This is the reciprocal.
Mm.
And I think arithmetically, we probably keep track of those in a better way. Here's where it really messes us up, because we use similar notation for both of these. Right? So this means my inverse. Right? Well, notice what happens. I'm going to show you. And when we get to trig, you're going to see this, and you're going to see this.
Mhm.
This, because it's attached to my sign, this is my inverse sign. So that means if I have 30 degrees, and then I put that into the sine of x, and then that goes into the inverse sine of x, I get back 30 degrees. So my inverse sine is mapping my sine ratio back to an angle. This is the reciprocal, which is 1 over sine of x, which is the cosecant of x.
Mm.
So we have to really pay attention to where is that -1 to know, am I talking about my inverse, or am I really talking about my multiplicative inverse, which is, or my reciprocal? That's a good question. And it's one of those sort of nuanced things because we use similar notation for both. But does that help clarify that?
Yeah. Yes. Thank you.
You're welcome.
I have a question as well. This is maybe very basic, but it reflects where I was a couple weeks ago when I was preparing our assessment for our Challenge A class. I loved the what are they? Suggestions, possibilities from the week 15 booklet. And one of the ones in there under illustration, I'm on chart 15.4. It said, create your own illustration to show that anything to the 0 power is always 1. And I realized that I have that memorized, that anything to the 0 power is always 1, but I didn't understand why. And so I could not think for myself how to even illustrate it. So I did some study on that and I feel more confident in it, but I'd love for you to show us and explain.
So there's a lot of really good explanations out there that I'm not going to remember, that people show graphically, that you've probably seen. But here's the one that I just saw that I thought was really clear, and it's also very classical because it supposedly belongs to Euclid. So supposedly Euclid said that I could take this and I could say that 0 could be a minus a, and this 0 could be some index minus some index. When we are dividing or subtracting indices, we could have written this as a minus a at the nth power over the nth power. And then we see that we have the same quantity in our numerator and in our denominator. And so in this case, we can more clearly see that that's 1. It kind of feels a little bit like Schrodinger's cat, right? Because we haven't simplified it yet. So it's 0, but we haven't written it as 0. So we can look at the unsimplified case and say, well, that makes sense that that's 1. There's a lot of people, myself included, that likes to think of this as when we think about the hidden 1, that anytime I have some number, I'm just going to use an example here, right? 5 squared. that my index is telling me the number of times I'm using my base as a factor, but there's a hidden one. I'm really saying it's one unit times 5 times 5. And so the first power of 1 would be 1 times 1, 5. And the 0th power of 1 would be 1 times no 5s. So there's different ways that we can look at that 0th power of 0. But those are probably two of the more common ones. Does that help?
Yes. Yep. That second one really helped me. Yeah. Thank you.
You're welcome.
Babs is saying the second one's easier for kids to understand. The thing that's so beautiful about the top one is it's true for every case, for NEA and for NEN. Hey, anybody else? Because we're almost out of time. Now's your chance.
All right. I am going to, okay, I'm going to skip our discussion question because we didn't need it, but I am going to put this up here. And because I wanted you to have something fun. So if you want to grab a screenshot of that, then you can work on that. Or Babs might be able to put that up on Facebook. And then you can work on that with your students and get a message from us. And notice that puzzles like this are really great things to do because if you know where your students have weaknesses, maybe there's some facts that they need to really practice. This is a way that you could choose the numbers yourself and choose the facts that you want your students to practice. And then it's sort of self-correcting, right? Because if they end up decoding the message, it's going to make sense to them and they'll know that they got everything right. And if there's something that doesn't make sense, then they know they need to go back and check their work. So, I'm going to leave that for a second, and then I'm going to assume that Babs has grabbed that, and we'll put that on Facebook. So if you're looking for it later today and didn't get a screenshot yourself, you can go look there. And then I found this prayer, and I thought this would be a great way to close out our time together. So if you don't mind me just praying this over all of you, I pray that you would all be filled with the wonder of Mary, the obedience of Joseph, the joy of the angels, the eagerness of the shepherds, and the determination of the Magi, and the peace of the Christ child. And I pray that God, the Father, and the Son, and the Holy Spirit would bless you all today and forever, and especially over our Christmas holidays. And I look forward to seeing you all in January.
Thank you, Kirsty. That was a really beautiful hour.
Thank you.
And may it be so with you, Kirsty, as well.
Thank you.
Mhm. Bye.
Bye.
God bless everyone. Merry Christmas.